Okay, for the beginning of this segment, we begin section 2.6, molecular and ionic compounds. These are two different types of compounds that differ in many of their properties. And the reason that their properties differ is essentially the types of elements that make up the compounds. You know, we've seen some elements are metals, some are nonmetals, some are metalloids. Well, how you combine different types of elements will determine the properties and the type of compound you get. So it's possible when you're combining atoms together to form a compound, essentially the way that you can form a chemical bond between these elements and get them to sort of bond together to form a molecule is that, well, the elements can transfer electrons from one element to another. So in other words, one would gain electrons and one would lose electrons, or they can share electrons. Those are essentially the possibilities. And that is really, when it comes right down to it, what determines the difference between ionic and molecular type compounds, whether they transfer electrons or share electrons. Also, many of the properties of the compounds will depend on whether the elements involved transfer electrons from one to another or just share the electrons between them. That situation, of course, can change during reactions, because what a chemical reaction is essentially taking molecules that have atoms bonded together in certain ways, taking those molecules apart and putting the atoms back together in different combinations. And if you put the atoms back together in different combinations, you might end up with different types of bonds. So before, you might have had a situation where the atoms were transferring electrons from one to another, but at the end of the reaction, you might end up with a situation where the atoms are all sharing electrons with each other. And that's one of the things that can change during a chemical reaction. Metals and nonmetals. Okay, so we'll get to this in more detail as we go through the types of compounds. So looking at ionic compounds first, we have to first address the idea of ion formation. So what is an ion, and how can you get an ion starting with a regular atom? Ions are basically atoms where the numbers of electrons and the numbers of protons do not equal each other. So for a given element, you'll have a certain number of protons. That number is also its atomic number, and that defines what element it is. And the atoms normally start out with the same number of electrons, so that there is no electrical charge overall. Oxygen will have 8 protons in the nucleus and 8 electrons around the nucleus. That's 8 positive charges and 8 negative charges for 0 charge overall. Then, though, the atom can gain or lose electrons depending on what else might be in the vicinity. And if it gains electrons, it becomes a negatively charged ion because it has more negative charges than positive charges. If it loses electrons, then it becomes a positively charged ion because the number of protons in the nucleus hasn't changed, but the number of electrons has gone down. So now you have one or more protons in the nucleus that don't have any electrons to cancel them out. And ion formation always involves gain or loss of electrons. The number of protons will not change in a chemical reaction, because if you're changing the number of protons, you're changing what element you've got, and that can't happen in a chemical reaction. So it's always gain or loss of electrons. And we just mentioned that metals, when they're reacted with nonmetals, tend to lose electrons. So the metal loses electrons and the nonmetal gains electrons. The result of that is that the metal, which loses an electron, one or more electrons, becomes a cation with a positive charge. And the charge of the ion for the metals, remember this is for metals, will just be the group number. That is the group numbers with the A after them. So if you're looking for something in, say, group 1, sodium, there's sodium in group 1A. Sodium tends to lose 1 electron and ends up with a charge of +1. And that's the same for everything else in group 1A also. If you did the same thing with potassium, you would find that potassium forms ions with a charge of +1 because it loses one electron. Too early for valence electrons. We haven't gotten to those yet. Calcium is in group 2A. See, right there, group 2A. Calcium will lose 2 electrons and end up with a charge of +2, same as the group number. And that would be the same for magnesium or strontium or barium or whatever, or beryllium or whatever else in group 2. Aluminum is in group 3A. And aluminum will lose 3 electrons and end up with a charge of 3, +3, just like the group number. When we represent things in the form of a chemical reaction like this, just remember that we're going from left to right. What we're starting out with, or the reactants, will be on the left, and what we end up with, or the products, will be on the right. And the arrow represents the reaction or the change itself. So here we're saying a sodium atom, you start out with a sodium atom, but you end up with a sodium ion with a charge of +1 and 1 electron. And so this is what you end up with. In other words, the sodium atom is producing an electron, or in other words, the sodium atom is giving off an electron. And another way of thinking of that is that the sodium is losing an electron. So if something is a product in a chemical reaction, you can think of it as being the reactant is losing that product. Calcium produces 2 electrons, which is similar to saying calcium atoms lose 2 electrons. They give them off to something else. And the same with aluminum, and 3 electrons. If you remember what the atomic number represents, the atomic number, remember, represents the number of protons in the nucleus of an atom. And as long as you're talking about a neutrally charged atom with 0 charge overall, that atomic number also represents the number of electrons that that element normally has. As you go left to right across the periodic table, the atomic number goes up by 1 for each space. So sodium to magnesium, atomic number goes from 11 to 12. That means from sodium to magnesium, the number of protons goes from 11 to 12. It also means the number of electrons goes from 11 to 12. If you look at sodium and you go back 1 atomic number, you end up with neon, atomic number 10. Neon only has 10 protons and 10 electrons. And if you notice what happens when these main group elements form ions, you'll notice that sodium, remember, loses 1 electron. So that means it still has 11 protons because the protons in the nucleus haven't changed. But in terms of the number of electrons, if it's lost 1 electron, the Na+ ion now has only 10 electrons, which means the Na+ ion has the same number of electrons as neon, 10 electrons. 11 protons, but 10 electrons. If you look at, say, calcium, calcium loses 2 electrons, which, as far as the number of electrons is concerned, is like going back 2 spaces in the periodic table. So with calcium, when it loses 2 electrons, it ends up with 1, 2, the same number of electrons as argon. So calcium atoms have 20 protons and 20 electrons, but calcium +2 ions have 20 protons and 18 electrons, the same as argon. Okay. In case you're noticing a trend here, you're onto something. Because if you look at aluminum, aluminum loses 3 electrons. So aluminum starts out with 13 protons and 13 electrons. So there's no charge overall. But if it loses 3 electrons, then the number of electrons will be 3 spaces back. 1, 2, 3. Or in other words, aluminum +3 ions have the same number of electrons as neon. notice how each time we form an ion, we end up with the same number of electrons as one of the noble gases. And there is a reason for that. That's because the noble gases, as I mentioned before, are very stable, very low in energy, and nature generally favors greater stability or lower energy. And so when you have something that's higher in energy, like a sodium atom, it will try to adopt a configuration, let's say, that will allow it to have lower energy. And one way sodium atoms can have lower energy is by losing an electron and having the same number of electrons as neon, because that is a very stable number of electrons to have. And so that's essentially what we're going for. The metals, or the main group metals anyway, will lose enough electrons to get you the same number of electrons as the last previous noble gas in the periodic table. And so this is what we were getting at here. Noble gas configuration. Loss of electrons leaves them with the same total number of electrons as the last previous noble gas. And that brings them greater stability. And so that's why they form ions with the charges they do. And so, like I said, sodium has 11 electrons because it's atomic number 11, but Na plus has 10 electrons, the same as neon, which has atomic number 10. Now remember, sodium is not becoming neon. It's just that basically sodium is kind of masquerading as neon. Sodium ends up kind of looking like neon from the outside, which is enough to make it much more stable. Sodium plus ions still have the sodium nucleus with 11 protons, but the fact that they have 10 electrons sort of allows them to masquerade as neon from the outside, and that makes them more stable. Calcium has 20 electrons because the atomic number is 20, but calcium plus 2 ions have 18 electrons, which basically means that they look like argon from the outside, and that is a more stable situation than when you have the neutral atom. And same idea with aluminum. All right. So the name of a metal ion is just the name of the metal plus the word ion. So Na plus, you can call it Na plus, or you can call it sodium ion. Calcium, you can call it calcium 2 plus or calcium plus 2 if you prefer, but calcium ion is also okay. With the main group metals, they only ever form ions with a single charge. So sodium, being in group 1, is always, the ions anyway, are always +1. And the same with all of the other elements in group 1A. And calcium, being in group 2, always forms ions with a +2 charge, as same with the other elements in group 2A. And aluminum always forms elements or ions with a charge of +3. Okay, and let's see, there is an illustration in the textbook. Don't have hard copy, but oops, there it is. You can find this one on page 100, actually. And you can see how the, it's a little blurry, I guess, but you can see how the ions in group 1 all have +1 charges, and the ions in group 2 all have +2 charges. And aluminum over there always +3. Notice the ones in the B groups in the center of the periodic table can take multiple charges depending on the situation, and we're going to get to those later, so don't worry about those yet. That's why I've been emphasizing we're talking about the main group elements here. Okay, for the nonmetals. The nonmetals are all in the A groups, so that helps. Nonmetals gain electrons from metals, and so nonmetals end up being negative ions or anions. And the charge on a nonmetal ion will be the group number, that is the group number that ends in A, -8. All right. So if we look at some examples, the charge on the anion, as I said, is group number, that is the group number that ends in A, -8. So if you're talking about, say, chlorine, it's in group number 7A. So 7 minus 8 is -1. You would expect the charge on a chlorine ion to be -1. If you're looking at oxygen, oxygen is in group 6A. 6 minus 8 is -2. You expect the charge on an oxygen ion to be -2. And that's exactly what they are. Chlorine is atomic number 17. And if it gains 1 electron, it will have 18 electrons, just like argon. Again, it's not becoming argon because it still has 17 protons in the nucleus, but it has 18 electrons. That one extra electron is why it has a -1 charge. And it also has the effect of making it kind of look like argon from the outside, which allows it to be more stable than if it had 17 electrons. And so chlorine will tend to gain 1 electron and become, will have the same electron number as argon. Oxygen has 8 electrons to begin with. And if it gains 2 electrons, it will have 10 electrons like neon. And that makes it much more stable. And that's why oxygen forms ions with a charge of -2. And for some reason, the habit has developed of writing the number first and then the sign. That is the conventional way to do it, but you could write the sign first if you want to. I'm not going to be picky about that. Nitrogen is in group 7, so it has 7 electrons, it's in group 5. Sorry, it has 7 electrons total. It's in group 5, and the charge on the ion would be 5 minus 8, which is -3. Or in other words, it gains 3 electrons to the point where it has 10 electrons, just like neon. So you can tell for a nonmetal, the number of electrons it'll gain is the number of spaces you have to jump to the right in order to get to the next noble gas in the periodic table. So from nitrogen, you have to jump 1, 2, 3 spaces. So nitrogen is going to gain 1, 2, 3 electrons. And therefore, the ion will have a -3 charge for nitrogen. And again, remember, nitrogen doesn't become neon. It still has only 7 protons in the nucleus, but it has 10 electrons, so it kind of looks like neon from the outside, and that makes it much more stable. Okay, and so that's basically what we just said. And let's see, naming of anions. For negative ions, that is ions formed from nonmetal atoms, the name actually changes. So for the metals, we have like sodium becoming a sodium ion. The name is the same. For the anions from the nonmetals, the name actually changes. And essentially what you do is you replace whatever ending the element normally has with IDE, normally pronounced ide. So for example, chlorine becomes chloride when it's a negative ion. So Cl is chlorine, Cl minus is chloride ion. You can leave out the word ion if you want, because chloride itself is the name of an ion, and it's kind of redundant to say chloride ion, but you can say it if you want to be clear. Oxygen becomes oxide when it takes a -2 charge and becomes the negative ion. And again, you could call it oxide ion if you want. Nitrogen with its -3 charge becomes nitride, or nitride ion. Carbon is in group 4, and you have to jump 4 spaces to get to the next noble gas. And so carbon will gain 4 electrons and have a -4 charge, and that's known as a carbide ion. Okay. And phosphorus becomes phosphide, And some of them are not entirely easily predictable. It's phosphide, not phosphoride. Sulfur becomes not sulfuride, but sulfide. And also spelling sulfur and sulfide with an F is kind of the American spelling, which is the most common one used today. But it commonly used to be spelled with a PH, which is the way they still do it in Britain and Australia and Ireland, and to some extent in Canada too. So if you want to spell sulfide and sulfur with a PH, that's fine with me. The noble gases themselves, since all of the other atoms essentially want to gain or lose electrons to get to the point where they have the same number of electrons as a noble gas, you might think, well, what do the noble gases do? And the answer is nothing, because they already have the same number of electrons as a noble gas, and they're already really stable. So they don't really form ions of any kind. Not normally, anyway. Something else we need to cover, as long as we're talking about ions, is the idea of the polyatomic ion. Polyatomic ion, if you think about the word polyatomic, poly is from a Greek word meaning many, and atomic refers to atoms, obviously. So polyatomic ions are ions that are made up of more than one atom at a time. We've been looking at ions here like Cl- and O2-. Each ion is formed from a single atom of an element. But it is possible to have groups of atoms that have a charge on them collectively and act sort of as a unit. So basically, polyatomic ions are like molecules that have electrical charges on them. Normally, a molecule has no electrical charge, but if they do have an electrical charge, then they're called polyatomic ions. So they're ions formed from a combination of more than one atom, like a molecule, but with an electrical charge overall. The charge belongs to the ion as a whole. It doesn't belong just to any one atom within the ion. And they tend to react as a unit, and they tend to remain intact during chemical reactions, usually, not always, but usually. And let's see, they are listed on page 101 in the textbook. And it's this table here, and that's still a little blurry. I'm not sure why. But anyway, you can look down the list, and these are the most common polyatomic ions. The most important ones anyway. There are lots of others. And one thing you might notice is that there are really only two positively charged polyatomic ions of any importance, ammonium and hydronium. And of those two, really ammonium is the only one that we really deal with a lot as such. And the rest are all negatively charged. So there's a huge number of negatively charged polyatomic ions. The names of the polyatomic ions are derived from the elements involved in them to some extent, or most of them anyway, but not always in a really predictable way. So this is a case where it kind of calls for some memorization. Memorizing the names and the formulas and the charges on the various polyatomic ions, that's something you're going to have to put some effort into, unfortunately. There are some rules for naming polyatomic ions. It turns out that most of the negatively charged polyatomic ions involve oxygen in some way, and those are known as oxyanions. And there are some rules, like for instance, what we're dealing with here with polyatomic ions is non-metal elements. If you look at that table on page 101, you'll see that all of the elements involved in all of those polyatomic ions are nonmetals. And one of the things we're going to see in greater detail as we go on is that when you're dealing with combinations of nonmetals, there are often multiple combinations possible. So if you're talking about combining sulfur and oxygen, there are several different ways you can do that. Whereas if you're talking about, say, combining sodium and chlorine, there's only one way to do it, NaCl, that's it. With the polyatomic ions, there are multiple possibilities. And so when naming a polyatomic ion, the general rule is, for at least for the oxyanions, the name is based on the name of the element that's present other than oxygen. And if it has the greatest number of oxygens possible, then it ends in ATE. And if it has the second highest number of oxygens possible, it ends in ITE. And a good illustration of that would be the sulfate ion, which has the formula SO4 with a collective -2 charge on it, versus the sulfite ion, which has a formula of SO3 with a collective charge of -2. So, that's nice to know, but not all that nice, because if you look at nitrogen and oxygen, you have nitrate, which has the highest number of oxygens possible for a nitrogen-oxygen type of oxyanion, but it's only got 3, and it has a -1 charge overall. And then you have nitrite, which has 1 less, NO2 with a -1 charge overall. So ATE ending means the maximum number of oxygens possible with the other element that's present. But how do you know how many that is? Well, you pretty much have to memorize it. There's also per and hypo that can be used in extreme circumstances where you've got a lot of different combinations possible for oxygen with another element. So for example, we've got the oxyanion that has a formula ClO3 with a minus charge, and that is known as chlorate, named after chlorine, and ATE indicating that it's the maximum number of oxygens possible with chlorine. There's another one for the formula ClO2 with a -1 charge, and that is called chlorite. But nature kind of threw a wrench into things here, because there is also a chlorine-oxygen anion with the formula ClO4 with a charge of -1. So what do you call that? You've already used the ATE ending. Essentially what they named it was beyond chlorate, using the prefix per. Per, PER, is a Latin prefix that just means through or beyond. And so essentially ClO4 is beyond chlorate. And there also happens to be an ion with the formula ClO with a -1 charge. But we've already used ITE. Now what? Well, what they did is basically they named it below chlorite, or hypo. Hypo, actually hypo comes from Greek, not Latin, and it means below. So hypochlorite means below chlorite in terms of the number of oxygens present. Sodium hypochlorite is the principal ingredient in bleach, by the way, just for some place that you might have seen it before. Okay, so the main classification of compounds has to do with whether the atoms involved in them will transfer electrons from one to another, and that's ionic compounds, or whether the atoms will share electrons between them, which is known as covalent compounds or molecular type compounds. And so to get to the general properties of ionic compounds, I'm going to actually leave it off there because we are at time for this video. And we'll have to start up with part C in just a moment.